We have introduced the recursive calls in the calculate fare function. So you would remember that calculate fare was actually making a call to itself. Let me go back to that function here. So we have this distance calculation example, or fare calculation example according to distance, which was initially checking whether the distance traveled was less than or equal to 10 kilometers. If so, it was returning some fare calculated according to these values. Okay. And if the distance is greater than 10 kilometers, it was making a call to the calculate fare function, which is the same function itself. So this is a recursive call to the calculate fare function. If a function is calling itself, this is called recursion. So there has to be some rules when you define recursive functions. So it's dangerous if you make a call to the same function here in the beginning. So if you make a call to calculate fare with distance, or let's say 10 kilometers, with values student, teacher, and senior. What this does is, in the first call to this function, calculate fare, it's going to make, so it's going to go in here. The next statement it's going to execute is calculate fare once again. So it's going to go back again into this function. What it's going to do is make a call to itself once again, and it's going to go here. So this is a non-ending function. So the danger of recursion is an infinite recursive call. So this function never ends in your computer. It executes until it exhausts all your resources, such as stack depth or memory allocated for your computer, or the computer may crash entirely depending on the situation. So this is a dangerous call. So when you enter the function itself, the first statement is making another call to the function itself. So this never ends. It just keeps repeating itself over and over until you come to an end in your memory, in your computer. So there are some issues that we need to take care of before we define a recursive call. And when we go into the recursive functions, for instance, we have a recursive factorial function. A recursive factorial function is, you know that factorial is, so 5 factorial is actually 5 times 4 times 3 times 2 times 1. So the 5 factorial is actually 5 times 4 factorial. And 4 factorial is 4 times 3 factorial. So this goes on and on. So whenever you want to make a call, a recursive call in your function, you could return the result to be factorial 5 is 5 times factorial 4. Okay, so this is the recursive call to the factorial function with the variable having the value 4. It's going to make a call to the same function with 3 and 2, and when it comes to 1, these conditions hold, Okay, this one holds. N is equal to 1. So it returns 1. And it does not make another recursive function call to the factorial. So this is a termination condition for our recursive function. The termination condition is where it stops the function being called over and over. So it gets a definitive result and returns that result to the calling function. So when it was called for factorial 2, it was asking for 2 times factorial of 1, which is 1. Now it has obtained the value 2 that it can pass on to the call of 3 times factorial 2, which is pending in the result list. It's in the execution stack. It's waiting for a result. So this has the value as 2. Now it can conclude that 3 times 2 is 6, which is sent to the execution stack as 4, which was waiting as 4 times factorial 3. Okay, this is now 6. It concludes that this is 24, which was being expected by 5 times factorial 4. Okay. Now this gets the result of 24, and when we multiply this we get 120 as the result of our factorial 5 function call. This is factorial 8, but I made it for 5. So when we make calls to our recursive functions, as in this case, you would see that making a call factorial 5, factorial 4 is going to start another branch of execution which comes to this point because n is not less than 0, n is not 0, and n is not 1. So it just skips over these two and comes to this part for n being 4. So it's 4 times factorial 3. It reserves this part, makes a call to factorial 3. There's no definitive result at the moment. So factorial 3 is actually 3 times factorial 2 according to this flow here. So factorial 3 is not 0, 3 is not 1. So it goes to this part. 3 times factorial 2. Okay, it writes this into the execution stack or execution hierarchy, and then it recursively calls this factorial function for 2 times factorial 1. N is 2 at this moment, factorial 1. When it comes to factorial 1, this line is not executed. This doesn't evaluate to true, so it jumps to this part, checks whether n is 0 or n is 1. This part returns the result of true, and so it evaluates to true, and the function itself, factorial 1 function, returns 1, as in this case. So when this result is obtained, so this is the first result that the program receives from the execution. This 1 is returned to this line. It was pending, waiting for this result. So it multiplies 2 by 1 and returns 2 to this line. And this line returns 6 to this line. And factorial 4 is calculated at the latest step, which is 24. So the execution goes from the innermost function call to the outermost function call. So these all have to be calculated before the previous stages are concluded. I think there's another example, Fibonacci numbers, as you would all know. So there's this Fibonacci series which calculates Fibonacci value of a number being equal to Fibonacci value of the number 1 less of the given number and plus Fibonacci of the number 2 less than the given number, as in this case. So Fibonacci of a number is the sum of Fibonacci of n minus 1 plus n minus 2. So in order to calculate the Fibonacci of 5, you would first need to calculate the Fibonacci of 4 and Fibonacci of 3. So when you make a call to the Fibonacci function itself, it would call this first for the value 4, which would then call this for 3 and 2, and then it's going to first call the function for 3, which is going to call it for 2 and 1, and then it's going to call it, the 2 is going to call for 1 and 0. This is going to return 1 due to this condition, and as soon as it obtains the value for this part, for Fibonacci 2, it's going to call Fibonacci for 0, which is going to return 0, and then the Fibonacci 2 is going to conclude that the result is 1, return it to the Fibonacci 3 execution. Okay, so the 3 is going to conclude that it has 1 for Fibonacci 2, and it's going to calculate for Fibonacci 1. So this was pending. The depth of our execution is depicted here for you. When we want to make a call for Fibonacci 4, it first calculates for Fibonacci 3, which in turn goes into Fibonacci 2 and Fibonacci 1, but before executing this one, it has to first go into the deepest calculation for Fibonacci 1, which it finds to be 1. So this is the first result we obtain from this execution, and this is the second result we obtain. So it concludes that Fibonacci 1 and Fibonacci 0 are ready, so it sums these two. This is the third operation, and writes this into Fibonacci 2 to be 1. So this becomes 1 after this summation, and after that we have this value in our hands. Now we need to calculate Fibonacci 1. So we have this actually. Okay, so this is calculated from these two, and this has the value of 1. So now we have the value 1. We need to calculate Fibonacci 1 because Fibonacci 3 is Fibonacci 2 plus Fibonacci 1. So this has the value of 1 returned from its execution. So this is the fourth result we receive, and this is the fifth result, so that we sum the two values, and then we assign this to Fibonacci 3 to be 2. Okay, so this becomes 2. This is the fifth statement. Now we go into Fibonacci 2 once again, because it is for Fibonacci 4. We need to calculate Fibonacci 3, which we have as 2. 1 comes from here and 1 comes from here. It has the value of 2. Now we need to calculate it for Fibonacci 2, okay, which is here. Fibonacci 2 is calculated as 1 once again. So this was the fifth statement that we calculate and assign to the weighting stack, weighting function call. And then now we are in the sixth operation to calculate Fibonacci 1. Seventh calculates Fibonacci 0 to be 0. Okay, these are the termination conditions. So we need two termination conditions in this case, because one of them is Fibonacci n minus 1, one of them is Fibonacci n minus 2. So if n is 2, we need to calculate Fibonacci 1 and Fibonacci 0. We need two conditions whenever we encounter the parameter to have the value of 2. Not easy to type. Okay, so when it is 2, it goes into the, it shouldn't go further in the call stack. So it shouldn't be calling Fibonacci 1 and Fibonacci 0. If we call it for Fibonacci 1, and if we didn't have these termination conditions, it would be calling this function recursively for Fibonacci 0 and Fibonacci minus 1. Okay, Fibonacci minus 1 and Fibonacci 0 is defined, but Fibonacci minus 1 is not defined in this number series. So we should stop at these points that when n is equal to 0, Fibonacci value is 0. When n is equal to 1, the Fibonacci result is also calculated as 1. So these are defined values. These stop our function in this conditional flow from reaching this point. Okay, these two conditions here stop our function from reaching to this point, so it doesn't make any further recursive calls which are going to result in undefined results, undefined numbers for Fibonacci series. Okay, there's this improved version of the Fibonacci call. So you would recall that we already have calculated values for Fibonacci 1, Fibonacci 1, Fibonacci 1. So we make a call to Fibonacci 1 3 times in our code for Fibonacci 4 calculations. If it was Fibonacci 5, there would be more calls to Fibonacci 1. So once I make a call to Fibonacci 1, I know that the result is 1. This is valid for Fibonacci 2 as well. So if I can conclude that Fibonacci 2 is 1, sum of 1 and 0, and I have made calls to Fibonacci 2 multiple times, so I could simply reuse this value I have calculated. This is not a problem for small numbers, but if you want to compute the Fibonacci of 1000, there would be multiple calls to these functions, Fibonacci 2, Fibonacci 3, and your computer is going to be processing all those values over and over. The result is not going to change. Fibonacci 3 is always going to be whatever it is, 2, okay, 1 plus 2. But it's not going to change if you calculate them over and over. You're going to make your computer busy with calculating the same numbers. So once you calculate the result for the Fibonacci function, let's say Fibonacci 150, you can use it everywhere you need it. For instance, if you call it for Fibonacci 151, you're going to need the value of this one. Also, you're going to need it for Fibonacci 152 as well. So these two use the same value. So once you have the value calculated in your hands, you can simply retrieve it from the storage in memory or disk, and then use that value instead of making this recursive call to Fibonacci 149 plus 148. Okay, these will also start the function call stacks like this. Okay, they're all going to make your computer busy calculating these numbers over and over. Instead, you can just store them in some area in your computer and retrieve those values from that part. Here I used a dictionary, but we will come to the dictionary later in our topics. It's a simple lookup table. You provide a key for a value, so the keys are unique in a dictionary. So Fibonacci 2 might be something like this. The Fibonacci of the number is going to be the result. So if the number is not inside the Fibonacci dictionary, so you make a number, you get a number as a parameter, and if it is 0 or 1, the result is the number itself. So Fibonacci 0 is 0, Fibonacci 1 is 1, so you know the result from the number itself. If that number is not in the key part of the Fibonacci dictionary, so I have defined my dictionary using the curly braces. Okay, so this initializes a dictionary. If that number is not included in the Fibonacci number dictionary, we just present these square brackets and provide the number as the argument to the Fibonacci dictionary. So this inserts an entry to the dictionary. The dictionary is very similar to our English or Turkish dictionary. So there's a key and there's a meaning for that key. The key is unique, but there can be multiple meanings to the same key or different various lengths of text corresponding to that key. It doesn't matter. There would be numbers, images, whatever it is, but the key part is unique in the dictionary. So this is an analogy for this Python dictionary, that you can insert values. This is the value, result is the value for keys in your dictionary. The number is the key. So I want the Fibonacci of 150 to have some value. I don't know what it is. Okay, we can calculate it. So whenever I ask the Fibonacci dictionary for the value, for the Fibonacci value of 150, it's going to retrieve me that calculated result without making further calculations, because it's already calculated and inserted in the dictionary. So you can retrieve that value simply by a lookup, as if it was in a database. If the number is not 0 or 1, it's going to jump to this elif part. If number is not in the Fibonacci dictionary, okay, it's going to calculate Fibonacci of this number -1 and number -2 to be the result. So it's going to first sum the two values and insert them into the result. And it's going to insert this result as the value of the key number to the dictionary. And if the number was not 0 or 1, or if the number was in the dictionary, not in means it is not present in that Fibonacci dictionary, but if it is present, this evaluation is going to be false. So it's not going to execute this part either. It's going to jump to this part. So the result is going to be Fibonacci value received from the Fibonacci dictionary using the index or the key as the number. So it's already stored in my dictionary. It would look like something like this. Fibonacci dictionary, whatever that is going to be equal to 150, 2 dots, and the value of that calculation. So if we say Fibonacci dictionary is something like this. For 3, we know that we have the value 2, okay, because we have calculated 2. Fibonacci 1 plus Fibonacci 2 is 2. They both have the value 1. So when we sum them, we have 2 for the key 3. In this case, I know that Fibonacci 3 is already calculated and present in my dictionary because of these conditional checks. They were initially calculated. So if I ask for the Fibonacci value of number 3, it's going to retrieve it from the dictionary using this square bracket operator. So if we use these operators on the right hand side of an assignment statement, it's going to retrieve the value from the dictionary. But if we use it on the left hand side, as in this case, if we use the expression on the left hand side of this assignment, it's going to change its value or insert that value to the dictionary. But if we use this operator on the right hand side of this assignment, it's going to retrieve the value. It's not going to insert, but it's going to read from the dictionary and assign the value to this result variable and output the result or return the result according to our function. So this is a very brief introduction to the dictionaries, just for practice. So you can go deep into this and probably write a different version for the recursive factorial or other recursive calls to your functions. So when you make a call to these various numbers, you can see that these lines are not executed. So these are not going to be executed each time you make a call to these values. If you wrote this function in the other way around, so at each step you make a new calculation for those numbers you already know, you would see multiple outputs for calculating those values. But in this case, Fibonacci value was previously calculated for number, returning the result from the dictionary, etc. And you all understand now what we're talking about. And going into this function, we can run it. See, the result is that it just makes one calculation for a number, and for the rest of those calls to Fibonacci calculation, it just retrieves those values from the dictionary as stated in these outputs. So this sums up chapter 3, that you can see all these operators and logics and recursive function calls. This is an advanced topic, recursive functions. We'll make more examples. Also, we are going to discuss about dictionaries and tuples and lists in more detail later in upcoming lectures.